For the first task this week, you were looking at series circuits and what happens to the current and the voltage in a series circuit. So just a quick reminder, in a series circuit, the current is the same everywhere. So it doesn't matter where you put the ammeter in the circuit, it'll always give you the same reading. So it's the same at every point in a series circuit. Okay, so in this example, it was 1 amps everywhere in the circuit. And in this example, it was 0.5 amps everywhere in the circuit. The voltage or potential difference, though, is slightly different. So remember, you've got your supply voltage, what you're getting from your battery or your cell. So 8 volts here, 12 volts here. That 8 volts has then got to be shared between all the components in the circuit, ignoring the ammeters because they don't count. So in this case, it's been shared between a lamp and a resistor. And so each one is going to get 4 volts each in this particular example. So what you've got here and here add up to what you've got up here. Okay. And in this example here, so about 12 volts from our cell. That 12 volts is to be shared between a variable resistor, a lamp, and another lamp. Now it could be 4 volts each, but it's not always shared exactly the same. And in this example, what we said was that the variable resistor was getting 6 volts and the lamps were getting 3 volts each. The key thing is it adds up to 12. Okay. What you have up here is always going to be your maximum. So that's series circuits. What we're looking at now is parallel circuits. So a parallel circuit is one where you've got more than one branch. There's more than one option for where the current can go. Okay, so look at this one first. So as the current's going down the circuit, our electrons are flowing in our circuit, they get to this point here, some of them can go this way and some of them can go this way. Okay, now in this example, both options are the same. There's lamps that we can assume that are identical on each one. So we've got 2 amps of current here. So what that means is that half of it will go this branch and half of it will go this branch. So the current now is shared between the branches. So 1 ampere, 1 ampere gives us a 2 in total. There's another example here. So we've got 4 amps at the top. So that's what we're going to start with and finish with. This time though, we've got 3 branches. So we've got a branch with a resistor, a branch with a lamp, and another branch with a resistor. So what's happening here is these components don't all have what's called the same resistance. And we'll talk about resistance next week. And it means that it's easier for the current to flow down some branches compared to others. So what happens this time is rather than it being even like here, what we've got is we've got 1 amp going this way, which then leaves us with 3 to come down here. At this point here, 2 go this way and 1 goes this way. So the current in the 3 branches, 1, 2, and 1, still adds up to 4. Okay. What you can then look at is you don't just have to have the ammeters at the start of your circuit or at the end of your circuit or on each branch. You can stick one in the middle somewhere too. So at this point here, we've got 3 amps because this 2 amps is going up here and so is this 1 amp going up here. Whereas this one isn't. That's never going to flow through that ammeter. Okay. So the electrons are either, our current that's flowing is either doing this or it's doing this, or it's going down to this branch and doing this. Okay. So that then means at this point here, we would have 3 amps because we've got all of the current that's gone from this branch and all of the current that's gone from this branch. Okay. The other key thing to remember or to know is that the distance from the battery isn't relevant. So when you set these circuits up, obviously you're going to use more wires down here than compared to up here. And that confuses people sometimes. They think that because they've got more leads and it's a longer distance for them to travel, that's going to make a difference to the current. But actually it doesn't. It's to do with what these components are. So that's current in parallel. It's shared between each branch on the circuit. Okay. Then we've got voltage in parallel. So voltage, remember, is kind of like the amount of energy that those electrons have got. So again, what you've got up at the top, that's the most you can ever have. So that's the amount of energy that the battery or the cell is giving to the electrons as they flow around the circuit. Okay. Now this time is the other way around to what we're looking at before. Electrons that go this way and go through this branch are only going through one lamp. So that means all their energy can go to that one lamp. So rather than it being shared this time, this lamp gets all 6 volts. Because the ones that are going this way only have to share it between that one lamp. So they get all 6 volts. The ones that are going this way also only have to go through one lamp. So they can transfer all of their energy to that one lamp, which means it gets 6 volts as well. Whereas if they were in series, they would get 3 volts each. But when you put them in parallel, they get 6 volts each. And when we connect lights up in parallel compared to series, they are much brighter. So same here. We've got 4 volts up here. So that means that the electrons that go this way have got 4 volts to give to their components. The electrons that go this way have got 4 volts to give to their components. Look at the bottom branch first. So those ones have only got to go through one lamp. So that lamp gets all 4 volts. Okay. The ones that go through this branch here, they have got their 4 volts, but they have to share it between 2 within that branch. So the total branch, the total voltage across that branch is still 4 volts, but it's shared between the 2 lamps that are in that branch. Okay, so they've got their 4 volts. They give 2 to this one, 2 to this one, back to get some more. Okay, hopefully that makes sense.